In this tutorial, we're going to take a look at, I'll call this applications of mathematical induction. We're going to take a look at a couple of proofs, non-standard, not proving series formulas using mathematical induction, and then also a proof of the binomial theorem using mathematical induction. So in this first example, we're asked to prove that n cubed minus n is divisible by 3. Now, if it doesn't state a particular range for n, then we will assume that this starts at n equals 1 and continues upward. So the first step is to show that it's true for 1. So if we put 1 in place of n, 1 cubed minus 1, we're supposed to just show that's divisible by 3. And of course it is. That's equal to 0, and 0 certainly is divisible by 3. So we assume that this is true for some arbitrary integer k. If we put k in place of n, our assumption is that k cubed minus k is also divisible by 3. And our goal is to show that no matter what k is, it's always true for the next integer after k, which of course would be k plus 1. So we want to show that if we put k plus 1 in place of n here, k plus 1 cubed minus k plus 1 is divisible by 3. Now, we'll start with this expression. I'm going to expand it out. So k plus 1 cubed is k cubed plus 3k squared plus 3k plus 1. So those first four terms are the k plus 1 cubed. And the goal of this tutorial is not to show how to expand a binomial to the power of 3. So you can do that separately. And then when we take the brackets off this, remember all those signs change, so it's minus k minus 1. Now the reason that this term and this term are red is I want to draw to attention that that's where the induction hypothesis, this assumption part, comes from. And so I'm just going to rearrange this with a k cubed minus k first, and then 3k squared plus 3k, the 1 and negative 1 of course add to 0. And so notice that the last two terms here have a common factor of 3. So I'm going to factor a 3 out. Now, by the induction hypothesis up, this is called the induction hypothesis, this assumption here, the k cubed minus k is divisible by 3 by that induction hypothesis. This is divisible by 3 because it has a common factor of 3. So that means that the entire quantity is divisible by 3. And so, since the statement is true for k plus 1, then n cubed minus n is divisible by 3 for all n contained in the natural numbers. Remember how mathematical induction works. Because of this assumption, we assume that for an arbitrary integer k that it's true, and we show that no matter what k is, it's true for the next integer. Well, some people have a problem with that assumption, but what that means is that, okay, we showed it's true for the first case, so this statement here means that if it's true for an arbitrary integer n, or k, sorry, and it's always true for the next integer after that, then if our one case is true here, then it's automatically true for 2, the next integer after 1. And if it's true for 2, it's automatically true for 3. And if it's true for 3, it's automatically true for 4. And you keep on going forever, which takes care of the entire set of natural numbers. That's how that mathematical induction idea works. On to another example, another one of these divisibility ones, and I'm going to show a slightly different way to do this one. This is another divisibility one. We're asked to prove that 7 is always going to be a factor of 23 to the 3n minus 1. So the first thing to do is show that it's true for 1. So we put 1 in place of n up here. So 23 to the power of 3 times 1 minus 1. And if you evaluate that, you get 12,166. Now, 12,166 is the product of 7 and 1738, so because I can run it as 7 times another number, that means that 7 certainly has to be a factor of that. So it's true for the first case. So we assume that now it's true that this is true for some arbitrary integer k. So 23 to the 3k minus 1 is, and this is how I'm going to write this differently than the first example, is equal to 7m. So it's a multiple of 7, so it's divisible by 7, or m is some natural number. And our goal is to show that it's true for the next integer after k. So if we put k plus 1 in place of n here, that 23 to the 3 times k plus 1 minus 1 is equal to, and I'll call it 7p. You shouldn't call it the same thing as this, because they're not the same value. So equals 7p, where p is some natural number. So we'll start with our k plus 1 step here. And I'm just going to first of all expand this 3 into here. So we have 23 to the 3k plus 3 minus 1. And of course, again, we have to involve this induction hypothesis up here. So, and this is maybe a little bit of, might seem like a bit of mathematical magic, but in order to be able to involve the induction hypothesis, I'm going to subtract 23 to the 3k, which is actually this base to the power of just the 3k part, and add 23 to the 3k. Doing that, I'm adding, subtracting the same term, so I haven't changed the value of this at all. It's in net, I've actually changed it by 0 because subtracting and adding the same number has a value of adding 0 to something. And the reason I'm doing that is so I can do some factoring to involve this induction hypothesis. Now, I'm just actually changing some colors here to try to point out that on the end here, 23 to the 3k minus 1, okay, there's the induction hypothesis. 23 to the 3k minus 1 is equal to 7m. So I can put 7m in place of this. That's how I involve my induction hypothesis. Now, so that certainly is divisible by 7 because it has a factor of 7 in it. Well, how is this divisible by 7? Looks like it's divisible by 23 because we have a base of 23 here. But what I'm going to do is do some factoring here. And I'm going to factor a 23 to the 3k. So it sees 23 to the 3k, 23 to the 3k is common to both parts. So I'm going to factor that out. And how that works here, remember when you're factoring, you actually, powers, you divide the factor into the whatever you're factoring it out of. So when you're doing that for powers, you just subtract the exponents. 3k plus 3 minus 3k would just be 3. You can always check factoring by expanding. If I multiply these together, the base is the same. 3k plus 3 gives me that exponent. And of course, 23 to the 3k minus 1 would give me 23 to the 3k minus 1. Now, 23 cubed minus 1, that might look familiar. That's what we had up here. That was 12,166. So that's equal to 12,166. And if you remember, that was 7 times 1738. So that certainly is divisible by 7. So we can common factor a 7 out of all of that. So it has to be divisible by 7. So it's true for the next case, the k plus first case. So that means that 7 is always going to be a factor of 23 to the 3n minus 1 for all n contained in the natural numbers. Okay, proof of the binomial theorem. And this is fairly long. It's on several pages, so because the binomial theorem isn't something really short and small. Now, we're going to show that, and basically the way the proof works is this. We're asked to show that this combination series formula is always going to produce the certain power of a plus b to the n. So if n equals 1, on the left side here, a plus b to the first, of course, is just a plus b. Well, we want to show that if we put 1 in place of n here, 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 that's going to generate the two terms a plus b. So if we put 1 in place of n, that's what it looks like. Now, r starts counting at 0 and goes to 1, so there's two terms, okay, which actually is those two. If we put 0 in place of r, then the first combination is 1 choose 0, a to the 1 minus 0, b to the 0, plus, and then we put 1 in place of r, so it'll be 1 choose 1, a to the 1 minus 1, and b to the 1. Well, 1 choose 0 is 1. A to the first, 1 minus 0 is 1, so this actually is just a, so we have 1 times a, and b to the power of 0 would be 1 as well. So 1 times a times 1 would just be a, so that's actually the a term. And again, this is 1. This would be a to the 0, which of course is 1, and then b to the first. This is 1 times b. So it just gives us a plus b. So that's just demonstrating it's true for the very first case. Now our assumption, and I'll reproduce this later on when we need it, is that this is true for some arbitrary integer k. So if we expand a plus b to the k, that's equal to the sum of the terms from 0 up to k of the combination k choose r, remember we're putting k in place of n, a to the k minus r, b to the r. And we want to show that if that's true, it's always going to be true for the next integer after k, which would be k plus 1, and that's what that would look like. Now, the a plus b to the power of k plus 1, Okay, we want to show that property is true from the previous page. That would equal a plus b to the first times a plus b to the k. And because if we have the same base here, we add the exponents, that's where the k plus 1 comes from. So I'm going to expand this a plus b in here. This is just this distributive property. A times this power would be this, plus b times this a plus b to the k would be this term here. Now, here's our assumption from the previous page. Now, notice my color coding. This is a plus b to the k. So this summation is equal to the a plus b to the k. So I can substitute that in place of this, and of course this here as well. This was my induction hypothesis, that the summation from 0 to k is equal to that summation. So if I expand this out, I have a plus b to the k is equal to, so I'm putting, I'm going to start with, of course, 0 in place of k, or sorry, r. So this would be k to k choose 0, which is this. And if I put 0 in place of r, this would be just a to the k, which is that term there. And of course, b to the power is 0, I wouldn't bother to put it in because it's 1, so that's why there's no b here. And then we put 1 in place of r, so k choose 1 would be this term. If we put 1 in place of r here, this would be k minus 1 for the exponent, and b to the first. And then 2, 2 here, 2 here, 2 here, etc. It keeps on going, of course, up to whatever k is. The last couple of terms, this is just a general term in the middle. The last term, of course, become from putting k in place of r. So that's why this is k choose k. If the exponent is 0, k minus k would be 0. Then a to the power 0 is 1, so that's why there's no a here. There actually is. It's an a to the power 0. And then b to the power of k. Plus, and then so that's that whole part right there, those two rows. And then b times, again, a plus b to the k. This is actually going to be the same thing. This and this are the same. So this whole series here is going to be the same as what I'm going to put here. And that's what we're expanding b into. Now, if I multiply a in here, okay, so the combination stays the same. A times a to the k, there's actually a 1 here. Remember, you add the exponents. So 1 plus k is k plus 1. If I multiply the a into this second term, when I add the 1 and k minus 1, you get k. This combination is the same, b is the same. When I multiply the a into the third term, when I add the 1 exponent here to the k minus 2, that's why this is now k minus 1. This combination is the same as this, the b squared is the same, etc. Right on to the very end. Of course, if I add a 1 onto this, this would be k minus r plus 1, which is that term there. And on the very end, when I multiply an a into here, that's why there's a single a on the end there. Otherwise, this term is the same. And we'll do the same with the b. When I multiply b into this term here, b combination k choose 0, a to the k times a b. And of course, when I multiply this b into this next term, that's just going to turn to a b squared, etc. And same thing all the way through. When I multiply b into this term here, when I add the 1 and the r minus 1, I get just r. Okay, remember 1 and negative 1 add to 0, so it's just r. And then b times b to the k would be b to the k plus 1, that from that term there. Now that's that whole series from the previous page. Now we're going to use something called Pascal's identity to simplify all this. And so I'm doing a little bit of rearranging here, noticing that this term here and this term here and this term here are actually like terms. They have an a to the kb, a to the kb. So that's the a to the kb. And so these two terms, the coefficients, are just the combination k choose 1 and k choose 0. So that's where those come from. Next, this next term and this next term are also like terms because they have the same variable part, a to the k minus 1b squared, a to the k minus 1b squared. And so I'm going to rearrange and combine them together. The two coefficients are k choose 2 and k choose 1 that we're adding here. Next, these terms that are kind of in the middle are like terms, so we'll combine those together. And then I'm going to show how to combine these terms together. So that's actually just an example of a few pairs of terms. Now, by Pascal's formula, if you're adding two combinations that start with the same first part, we often call it the n term. It's actually n minus 1 in this case in Pascal's formula. And the two second parts of the combination differ by 1. So this is r and this is 1 less than r. Then those two combinations add to and choose r. So notice that the second number is the same as the bigger of the two r's, and the n part is 1 bigger than each of these. We're adding two smaller. If you remember Pascal's triangle, this is actually what you're doing when you add two numbers and get the number in the row below. So if I were to add, for example, I'm looking at these two here, k choose 0 and k choose 1, for example. K choose 0 and k choose 1, notice that the first parts are the same and the second differ by 1. So this would equal the combination, and the first part would be 1 bigger than the k's, so k plus 1, and the same as the larger r value. Okay, so that would equal k plus 1 choose 1. K choose 1 plus k choose 2 would equal k plus 1 choose 2. In general, k choose r minus 1 plus k choose r would equal k plus 1 choose r, etc. So we can combine all these together. So for example, the sum of these two is the k plus 1 choose 1. The sum of these two would be k plus 1 choose 2. So I can rewrite this whole thing and simplify it using this Pascal's formula identity. And then, of course, there's one more as well, a couple more. So now it's difficult because you can't look back and see the previous page, but basically I'm rewriting this and combining those together, these together, etc. And so this is what it looks like. So this is what that whole series simplifies to. And this is actually the k plus 1 step. That we're trying to again show that a plus b to the power of k was equal to this summation. So if we were to start with 0, we would get k plus 1 choose 0, which is this. And if r starts at 0, this is a to the k plus 1. And of course b to the 0, there's no b term. If we put 1 then in place of r, k plus 1 choose 1, and this would be, if we put 1 in place of r, then this simplifies to 0, and we just get a to the k and b to the first, etc. On to the very last term, if we put k plus 1 in place of r, then the combination is k plus 1 choose k plus 1, which is this combination here. And if we put k plus 1 in place of r, then k plus 1 minus k plus 1 would be 0 for the exponent of a, so there's no a term. And then b would have an exponent of k plus 1. So that just does verify that it's true for k plus 1. So it's true for k plus 1, so then a plus b to the power of n is always going to equal this formula, and the binomial theorem is proven to be true. And that's the end of the tutorial.